right, friends, so Unit 2 is going to be all about, hold on a second. There we go. Unit 2 is going to be all about describing different types of density curves, and we're really going to be focusing on normal distributions. So that's where we're going to start our exploration today. And we're going to look at how to compare data using z-scores as well. So a little vocabulary before we get in. We have population, which is really the group that we're trying to learn something about. It's the group that we're trying to study, basically. In this an example of that might be all of the students here at Lake Braddock, whereas a sample are a few people selected from that group of interest, usually the ones that we actually collect data on. And that would be, an example of that might be 50 randomly selected Lake Braddock students. Now, whether those students are randomly selected or not randomly selected, they would still be considered a sample. It's just one would be a biased sample and the other would be a less biased sample. Now, if we are able to collect data from all individuals, we would call this a census. And again, that means we have data from every single individual in the group. Censuses are a little bit difficult to run and can be very costly, so we don't often use a census. Oftentimes we'll use a sample to make an inference about the population. But, for example, if I wanted to know the amount of time my first period spent studying for the Unit 1 test, if there's only 31 students, then it's easier for me to collect data from all 31 individuals and therefore create a census. Now, when we take actual observations or we take our sample, the notation for our mean is going to be an x bar, and the notation for our standard deviation is going to be s sub x. Whereas, if we're looking at a density curve, which is like an idealized shape of distribution, this is what we imagine the entire population looks like. Or if we take a census and collect data from the entire population, our notation for a mean would be mu, and the standard deviation would be sigma. So again, for our sample, mean is x bar with a standard deviation of s. Mean is going to be mu with a standard deviation of sigma. Now, as we go throughout this class, you're going to notice that our population is going to be using Greek letters, while the sample is going to be using English letters. So our formulas for this, well, when we're talking about means for populations and means for a sample, it's going to be the exact same. We're going to take all of the data values, so x sub I means every data value. We're going to sum them up, and then we're going to divide by the number of individuals in the sample. For a mean, or for a population, it's going to be the same thing. Sum up all of the data from the entire population and divide it by the number of individuals in the entire population. However, when we're talking about standard deviations, it's going to be a little bit different. So for our standard deviation for a sample, we're going to be taking each of our data values, subtracting by the mean, squaring it to turn it positive, summing all of these up, and dividing by n minus 1. Where for the population, we'll be dividing by n, and then taking the square root to undo this squaring. Right? So the reason why we divide by n minus 1 with a sample standard deviation is oftentimes in statistics, we're using the sample standard deviation as an estimate for the population standard deviation. Well, the issue with that is the sample standard deviation is probably not the same as the population standard deviation, so there's an unknown there. There's a little bit more variability because we don't know if we have the correct standard deviation. So to compensate for this extra variability, for this extra unknown, we make our denominator smaller, making our standard deviation bigger. So we're more comfortable overestimating what the standard deviation is than underestimating it, and therefore we make sure that this value is larger than the calculation would be if we had every single data value. If we use our calculator, we can do 1 var stats. We have our x bar. Now, whether we've taken a census or not, this x bar is going to be our mean value. So it uses x bar, but it could actually be mu as well. If we have a sample standard, or if we have a sample, the standard deviation we would use is S sub x. If we've collected data for the entire population, we can use that sigma x here. Notice that the sample standard deviation is always going to be bigger than the population standard deviation. Now, what we're going to be focusing on this unit is a density curve that is very special, going to be very, very powerful as we move through this course, and that's going to be a normal curve. Now, normal curves are symmetric, so using a mean for the center and the standard deviation for the spread is appropriate and actually going to be extremely useful to us. We're going to talk about why that is as we move through this unit. The notation that we can use when we have a normal curve is using n, with the first number inside the parentheses being the mean and the second number inside the parentheses being the standard deviation. So n mu comma sigma. When we draw our standard normal curve, we'll often denote 3 standard deviations to the right of the mean and 3 standard deviations to the left of the mean. So for our first example, let's take a look at a normal distribution with n 16,4. Again, 16 is going to be that mean, the center of our data. And then we're going to go 3 standard deviations to the right, adding 4 each time, and 3 standard deviations to the left, subtracting 4 each time. Now, when you're drawing your normal curves, you do not have to write this minus 4 and this plus 4. You can just write the numbers below. Take a moment and pause the video and see if you can sketch a normal distribution of n negative 5, 2. Right. So our n negative 5, 2 gives us this, so we'll have negative 3, negative 1, and 1. You don't need to write those plus 2's on the right, and negative 7, negative 9, and negative 11 on the left as we subtract 2 each time. Again, don't need to write that minus 2. Third example is we have the battery life of Duracell batteries that are normally distributed with a mean battery life of 42.3 hours and a standard deviation of 8.2 hours. And we want to sketch the normal curve. Now, in this case, we're sketching a normal curve with context, so we need to make sure we label our axis. So we're talking about battery life in hours. Our center will be 42.3, and we'll go 3 standard deviations to the right and 3 standard deviations to the left. Now, another really powerful tool that we can use is the standard normal curve. Okay? And the standard normal curve is a normal curve that's represented by capital N 0, 1, or N 0, 1. So our center is 0, and then we count 3 to the right and count 3 to the left. Now, the reason why it's going to be so powerful is because if we change our mean of a normal distribution by subtracting or adding numbers to all of the values, then we can move the center. Okay? We can also change the standard deviation of a distribution with the mean staying the same so that we could make it wider and more narrow. Okay? But not changing the center. We could also change both by adding, subtracting, and multiplying and dividing. Okay. Now, how is that going to help us? Well, let's take a look at this scenario right here. Okay, we have SATs and ACTs are normally distributed, and we want to sketch the distribution for both scores. So we plot our values for the SAT data with our center being 1050. For ACT, our center being 20, and then go 3 standard deviations to the left and 3 standard deviations to the right. Well, what happens if we have 2 students who are both applying to VCU with only 1 spot left? They're going to use their test score. They decide they're going to use their test scores to determine who gets the last spot. So Emily took the ACT, got a score of 27, and Amy took the SAT and got a score of 1320. We want to know who did better compared to the other. Well, they're different tests, so how are we going to compare that? Well, we can compare that using a z-score. Basically, what we're going to do is manipulate those normal curves so that they become the standard normal curve. Well, how can we do that? Well, if we take all of the data values, or in this case the one that we care about, and subtract it from the mean, that would move our mean over to 0. Right? Then or find the distance from our data value to the mean. If we then divide that by our standard deviation, then that means that we're figuring out how many standard deviations we are from the mean. So again, our x in this scenario are going to be the actual data values. Mu is going to be the mean of the population, or in this case our density curve, our idealized curve. The standard deviation, or sigma, is going to be our standard deviation of the population, or our idealized shape, our theoretical shape of the population. And again, that z-score is going to tell us how many standard deviations we are from the mean. If the z-score is positive, if this value is positive, our standard deviation is always going to be positive, so that means that x is bigger than mu, meaning that that data value was above the average. If it's negative, that means that x is less than the mean, which means that our data value is below the average. So let's calculate the z-scores for each of those individuals. And so, whoops, I forgot to change this value right here. I'll make sure to change that on the notes that I post online. But pretend this is 1320 and that this is 1050 and this is 150. Over here, we have the correct values. So we have a z-score of 1.8 and a z-score of 1.7. Okay. So when we plot those, Emily was 1.75, Amy was a 1.8. So which student did better and should get the top spot? Well, that would be Amy, right, with her 1.8 score. Okay. Let's take a look at another example. Mary and Rob both ran the Marine Corps Marathon. Mary had a time of 4.21 hours, while Rob ran it in 4.08. The women's division had an average time of 4.68 hours and a standard deviation of 11.6 hours. The men's division had an average time of 4.27 hours with a standard deviation of 17.9 hours. Excuse me. We want to know who ran it faster compared to each other. Well, Rob ran it faster, right? He had a slower time. Or he had a quicker time, I should say. He had less time to run the marathon. Take a moment and see if you can figure out who ran it faster when compared to their group. So pause the video and figure that out. All right. Now, when we're comparing two different groups, we're going to standardize them using a z-score. So again, for Mary, she ran it in 4.21. The mean for the women's division was 4.68, and the standard deviation was 11.6. So we can plug that into our z-score formula and find that she was 0.04 standard deviations to the left of the mean. Rob, on the other hand, ran it in 4.08 hours. Men's division had a mean of 4.27, but a higher standard deviation of 17.9. So when we calculate out Rob's, we find that he was 0.01 standard deviations to the left of the mean. So Rob, again, Mary was 0.04 standard deviations below the mean. Rob was 0.01 standard deviations below the mean. So when compared to their group, we want a smaller z-score because we want that time to be smaller, meaning that you are faster. So Mary ran faster compared to her group. So there are going to be times where a positive z-score is quote-unquote better, and there are going to be times when a negative z-score is quote-unquote better. So take a moment and think about a time where it's good to have a positive z-score and where it's good to have a negative z-score. When you're done, you can share with your partner. All right, so CNN collected data regarding the percentage of registered voters who voted on Election Day. The data turned out to be normally distributed, and here are the z-scores for our different states. So when we plot all of these, We want to know which states' z-scores are above the average. Well, any positive z-score, right? So we have Virginia, and we have California, and we have Alabama. Which state's z-score were the same as the average? Well, that would mean that we have a z-score of 0, because we're 0 standard deviations away from the mean. So that would be Missouri. And then the states that are below the average are our negative states, so Wisconsin and New Jersey. Right, I want you to take a moment and see if you can figure this out. I'm not going to post the answers on this video. You can check the PowerPoint when you're done. So I hope you found this video helpful. This is a little exploration of how we can use z-scores and how we can use normal curves to kind of compare data from different groups. Thanks.